Thank you, everybody. Thanks for inviting me. I'll be talking about a topic modeling approach for rank aggregation. This is joint work with our graduate student Wei-Kong Ding and a faculty member Prakash Ishwar. And so this talk is kind of like Devavrat's talk. In fact, it resembles his previous work that he did in 2009, I believe. And we have sort of followed on that type of work. It also has users and items and things like this. And hopefully I'll confuse you more by the end of this talk. Okay. So what is the main contribution of this talk, at least the take-home message, if you completely get lost in all of the modeling details and things like that? There is this entire field now that has been developed called topic modeling. What we are going to do is to suggest a new generative model for ranking and comparisons and things like this. And we want to show that hidden inside rank aggregation problems is nothing but a topic modeling problem in disguise. So our first task is to just show the equivalence between rank aggregation problem and the topic modeling problem for pairwise comparison. So that will be my first task. Hopefully I'll be able to convince you about that. Then what we want to do in this rank aggregation problem is to capture the fact that the users are heterogeneous. Just like Devavrat's example, different people had different likes and dislikes, so we want to capture the heterogeneity. And at the same time, we want to also capture the erratic behaviors of different users, which means they could be inconsistent and they could rate the same two items in different ways when offered the same two items. Okay? So if they like movie 1 versus movie 2, if you offer them, there may be a small probability that they may switch. Okay, so that is another thing that we want to point out. Now, this will lead to a new generative algorithm, and this new generative algorithm, hidden behind all of these algorithms, is this idea called latent variable models. So there are things, what you observe, it can be modeled as something latent, coming out of latent mixture of latent things. And when you have these types of latent models, automatically there is something called separability that emerges. This notion of separability then leads to a specific extreme point finding algorithm that can be generalized across these different types of latent variable models. So we can exploit this geometric structure of these latent variable models to actually get polynomial sample complexity and computational complexity for extracting and estimating, predicting, and things like that from these user item systems. And eventually, these could also be used for recommendations. Okay? And then we will show empirical performance on is exactly movie lens data set. Unfortunately, that appears to be the one data set that is publicly available, so everybody uses that. So we'll be showing some performance on that. Okay. Okay. So I'm just explaining what a topic modeling is for those of you who have never heard of topic models. So you have a text document, and from that text document you extract all of the words, and how this is extracted is itself a different subject that I do not want to get into. But somehow important words from this document get extracted, and once they get extracted, these are the words. So these are the different words. So topic is simply a set of words and their frequencies. So there are different counts of these words in this text document. So this is your observation. This is kind of always your observation that you have to be aware about. Now, once you do that, what you have a fundamental model which says that the counts that you observe is a latent mixture of some underlying topics that you do not know. And the goal of topic modeling is to figure out these topics where topics themselves are a distribution over words. So you want to express these counts as though coming from a latent mixture of these topics that you have to determine.
What does latent mean?
What does latent mean? Latent means hidden.
Okay. Right.
Meaning something that you have to estimate. Latent means hidden. So a document here is a mixture of hidden topics, okay, where topic itself is a distribution over words. Okay, so what does this have to do with rank aggregation problems? So in rank aggregation problems, you have user preferences. Using these user preferences, you can lift them to the notion of a word. What is a word? I can think of a word as a comparison between any two movies. So I have movies here, and these are two different movies, and this particular user rates this movie over that other movie, which means that you have these things called counts, exactly as you have counts in the previous topic modeling situation. Now, underlying these counts, how these counts emerges, we can also come up with a generative model, which we can call as influencing factors. So some users may be overly influenced by an actor. Some users can be influenced by the fact that there is a movie. Some others could be influenced by something called special effects. Okay, so those are different types of influencing factors that lead to these comparisons. What you get to observe are only these user preferences. From those user preferences, you get to observe these comparisons for each user. Okay, so we can see what emerges. You can lift every user to be a document, as in a topic model. You can lift every word to be a comparison, and the number of times these comparisons go one way or another to be the counts.
Question.
Yeah.
So there is no notion of anti-word, right? In the sense, 1 greater than 2 versus 2 greater than 1. You're losing that information.
We'll get to this point. Yeah, we do incorporate it. Just for simplicity, I'm mentioning this. Yeah. Okay, so let's go back to what is the model. Okay, so let me at least try to explain what's the topic model. So here are all the words that have been that we have counted. So this is number of times DNA has been described, number of times genes has been described, and so on. These are frequency patterns. Underlying these frequency patterns in this document is these different actual probabilities with which those words occur. So these are documents, and the documents are producing these counts, and these are m different documents. A topic is a mixture of these different words. So for instance, genetics leads to one kind of frequency of different words, whereas data leads to a different frequency of words. For instance, the word DNA could appear much more frequently in topic 1, whereas word data could appear much more frequently in the thing. So by a topic mixture or a latent mixture, one means that you're only given this guy, and your task is to determine this decomposition between this and this. So each document is a different mixture of these different topics, and different documents constitute different mixtures. Okay, so you are given this particular matrix, and from this matrix, you should determine this and that. Okay, so now the question is, how does this relate to our rank aggregation problem? Okay, so first of all, we need to figure out what does one mean by a topic matrix, like we did for the topic modeling problem. So in the topic modeling problem, it's fairly clear what the topic matrix means. Okay, so for genetics, you have different frequency for these words. In data science, you have different frequencies for those words. So what does it mean in the case of for the ranking problem? So again, there are different topics. The topics are going to be different amounts of, basically each component of this topic is going to be the probability a movie 1 is preferred over movie 2. And so the ranking matrix is, each column is like a topic, and you have number of ordered pairs q times q minus 1, and you have k equals these number of topics. Okay, so this basically is pretty straightforward. Now the question is, how do you generate such a topic matrix? So you need a generative mechanism, and the generative mechanism can be one of two ways. One is called as the sampling, which is from the space of permutations, and that goes to Himanshu's question, which is it only goes one way, right? So here I'm comparing 1 versus 2, 1 versus 3, and I'm noting down this as a binary matrix. So I get, so what is each topic, right? Each topic is a permutation over all the possible different movies, and from that permutation, I'm going to get you all the binary comparisons. 1 means 1 is bigger than 2. Here means 1 is bigger than 2, and 2, 1 actually is 0. So if I rated 1, if this particular ranking rated 1 bigger than 2, and it necessarily means 2 is getting rated less than 1. So we can come up with a noisy version of this case, which is what is called as the Mallows model. So you have k different permutations to start with, and then you can make it noisy. How do you make it noisy? You take every 2 items at random and then flip a coin with probability p, and if it gets flipped, you switch it and get a new permutation. Doing it this way means that you have a distribution over these different permutations. So you get a distribution over these different permutations, and if you work it out, it turns out to be this distribution. So if you were to adopt the Mallows model, which is what we adopt, then each one of these components is the probability one gets rated greater than 2 given this baseline permutation sigma 1 and this baseline dispersion parameter phi1. So as you can see, as phi goes to 0, you get much more purer structure, and as phi goes to 1, you get completely random structure. Okay? So that's how this works. So then everything is kind of clear, right? So we used to have documents, topics, and these different mixtures. Now you end up with users. Each user is a different mixture of these different ranking or noisy rankings as in the Mallows model. So the goal simply, so one thing that I want to mention is that you are, by doing this, you're capturing both heterogeneity across different users. Why? Because different users here have different mixtures of these underlying rankings. And you're also incorporating inconsistency between users. Why? Because the way the model works is that once you get A11, you toss a coin, and with probability A11, you would rate 1 bigger than 2, and 1 minus A11, you would rate it the other way around. Okay? So you essentially have this matrix, which is the column equals pairwise counts of a user, and then the number of times user M prefers I over J. Once you're done with that, your goal is the following. You want, given X and K, you want to estimate all of these different parameters, which is matrix factorization, and also do inference and prediction. What does inference and prediction mean? Inference means that I want to compute which mixture applies to every user. Prediction means when I have new users, how do I predict, like what Devrut is talking about for a new user. Okay? So just to put this thing in comparison to all the other work that is in literature, there's been a lot of work in the last 10 years. So there is work based on single ranking models. So you only have one particular column in this column matrix. So everybody shares this ranking. And the goal is to just find out this ranking. You have a mixture of ranking models, which have been, so Devrut here looked at these kinds of problems over the last year. And we have been looking at both multiple shared rankings across different users. So our work is very closely related to Farias et al. In NIPS 09. And the main idea here is that we are using mixture of Mallows model, which leads to approximate separability that I'll point out in a few seconds. The main advantage of our model is that from a computational standpoint, we get polynomial complexity in terms of computation, and we get polynomial complexity in terms of sample complexity in discovering these different things. So this is the problem, and often one talks about a plate model such as this, and the plate model is basically all that I've described so far, so I won't get into the details again. The main thing to realize is that you can show complete equivalence between topic modeling and rank aggregation by associating the number of words to be the number of ordered pairs between different items, the number of latent rankings to be the topics, the number of users is the same as number of documents, and the number of comparisons per user. Okay, so this gives you a statistical equivalence between rank aggregation using pairwise comparisons and topic modeling. Okay, so this is an important point that I want to mention because this leads to a computationally tractable algorithm. So it turns out that whenever we have these kinds of latent models of generating documents, that this notion of approximate separability emerges naturally. So what is the meaning of approximate separability? What approximate separability in this context means is that if I take this ranking matrix, which is this beta matrix, and look at different rows of this beta matrix, then there exists at least one row corresponding to every topic such that it is predominant. So for instance, the comparison 1, 2 dominates for topic 1 over other comparisons. So beta 1 is much larger than, so if 1 gets rated higher than 2 in other topics, 1 does not get rated higher than 2 for these other topics. So approximately separable just means that there exists at least one comparison which is predominant for each factor. So here are 3 different possibilities. This kind of makes sense. Let me argue why it makes sense. Consider the extreme case where lambda equals 0. So when lambda equals 0, it means that a novel comparison is unique to each topic. So let's try to understand this. Supposing musical is an underlying topic, which is the influencing factor, then the fact that Sound of Music, which is a movie, is bigger than Terminator gets rated in one way because it's a musical topic, whereas in the action topic, it never gets rated higher than Sound of Music because Sound of Music is not rated higher than Terminator because Terminator happens to be the action topic. Okay, so this is a relaxation of this setting. Okay, so this is a formal result. What we are able to show that under our generative model, if the number of items Q is fairly large, then you typically get approximate separability, which means that you will have a beta matrix such that there are at least a certain set of rows such that every topic has a dominates over all the other topics for that particular comparison. And you can actually do Monte Carlo simulations with our generative model and actually see that even for fairly small number of items and topics, you do get this kind of behavior where you end up with different notions of different amounts of separability. Okay. So how does this separability idea? Yeah.
There's a formal statement there. What?
This is the statement. Probability that sigma is lambda separable. Lambda is a number. And probability that lambda separable is 1 minus k times the exponent of minus q. Q is the number of items times this number L. L appears to be log of lambda by log of phi to the power minus 2 to 2k. Okay. So as the number of items are sufficiently large, I mean, this is a loose bound. Actually, we could potentially improve this bound. But if this particular statement is saying is that if the number of latent factors grows logarithmically with respect to the number of items, then you typically see this type of behavior. Okay. So why does this separability help us? The separability helps us because if you look at A equals beta times theta, then what happens if you look at the different rows of A and look at the convex hull of the different rows of A, there are going to be rows of A which look pure like this, theta 1, theta 2, and theta 3. And all the other rows of A are convex combinations of these particular rows. So separability immediately implies that you get a picture like this. Each comparison, which is novel, that means that it is compared one way, is going to be the extreme points of the rows of this A matrix. So every time you get the separability, you will get approximately this picture. That is, there are going to be these novel comparisons which are going to be extreme points of these rows of A, and every other comparison is going to be inside this row of A. You can see this from A equals beta times theta, and if you have, for instance, this ranking matrix, which is a binary matrix, then 1, 0, 0 corresponds to theta 1 here, and then 2, 1 is another novel pair, and it corresponds to theta 2 there, and 3, 2 is another novel pair, which corresponds to theta 3, and all the other rows of A are just convex combinations of this. Okay? So you end up with this picture every time you are able to establish that things are approximately separable. So now to just estimate the beta and theta matrix is simply to figure out the extreme points of this picture. Okay? How do you estimate the extreme points of this picture? Which directions to use? You simply generate PIID isotropy directions. So you generate directions at random and then look at what comparisons lead to the maximum value, what comparisons lead to the minimum value, collect all those comparisons, and those exactly correspond to the extreme points, and so you now have the extreme points. From there you can find the convex combinations for all the other different comparisons. Okay? So why is this robust? Well, and why does it work for the approximately separable case? Because the solid angle subtended by the extreme points is going to be always much larger than the solid angle subtended by the convex combinations. So because the solid angle subtended by this, most of the time you're going to get a hit that this is a maximum point, and very few times are you going to get a hit that this is a maximum point. So by just looking at sorting the k different counts and sorting them, you're able to figure out which ones pop out and which ones don't, and that turns out to be the k different rankings that you could figure out. Okay, so this is another result. Again, this is a theoretical result which says that the computational complexity in trying to figure out the beta theta matrix, it grows linearly with respect to the number of users, linearly with respect to the number of comparisons per users, and the number of random projections that you ought to do in this context. Okay, and this is the sample complexity, and this is stated in terms of lambda being sufficiently small, that is, lambda is approximately separable, but then as q goes to infinity, you can prove consistency because this is always satisfied for our generative model. Again, the number of users, as long as it grows polynomially with respect to the number of comparisons and the number of different rankings, underlying rankings, we are guaranteed that you will definitely figure out the beta and theta matrix with high probability at least 1 minus delta. Okay, where delta appears here, log of 1 minus delta. Okay, so I don't know how much time I have, but just a minute. Okay, so let me actually show one thing and then perhaps end this. So this is a problem. So this is the movie lens data set. So remember that I was telling you that it's not about just estimating, but we can also predict how new users will perform. How can we do that? Once we have the beta and theta matrix, we can then generalize to new movies and new users. For instance, if I get a new movie, then I can ask you the question, what is the probability that this particular movie has a certain rating? So for instance, if there are five ratings, star 1 rating, star 2 rating, star 3 rating, star 4 rating, and so on. So I can ask the question, what is the probability, likelihood, that this is a star 4 rating? How does that relate to the problem? Because it induces certain comparisons between certain other movies in the data set. So therefore, you can compute the likelihood, and once you compute the likelihood, you can then determine basically the recommendations for those users or for those movies for a particular user. So what this chart tells you is that if you follow the Bayesian approach, there's a well-known approach called Bayesian matrix factorization approach. then and you compare it, which is supposed to be the state of art, if you compare that against our approach, which is this MMMM, which is mixed membership model that I'm talking about, we get very comparable performance, although we are not using any Monte Carlo simulations here or anything. Our solution is very simple. We proved that it is approximately separable. Given that it is approximately separable, we just used random projections to find which comparisons are dominant. Using that, we figured out the beta and theta matrix. And once we figured that out, we can now predict for new users. And that gives you very comparable performance to the state of art. Okay? So let me conclude by saying that we have looked at high-dimensional mixed membership models. And in these high-dimensional mixed membership models, there is a geometry, which is approximate separability, which one could exploit in this context. So this gives you a very simple geometric picture, that is this kind of a picture. And this geometric picture directly suggests an efficient randomized algorithm, which is parallelizable and distributable. And from there, you can get consistency, efficiency, and state-of-art performance. Thank you.
Question?
Yes.
Interesting. The big question that I have is, how do you know when Q is large enough in order to get the separability?
That's a good question. So we can come up with bounds. We can come up with bounds for how large Q has to be, but those bounds may not be satisfied.
Are those bounds dependent upon the particular matrix?
No, those bounds are dependent on the generative model. So given this generative model, you can come up with bounds, right?
So presumably you could do some sort of.
So in the topic modeling, we exactly have these bounds and much more. The problem with ranking is that there's a huge correlation across these different comparisons, which makes the bounds kind of loose. But in the topic modeling context, you indeed. And interestingly, what happens is we have looked at the way people actually solve like latent Dirichlet allocation, which is a topic modeling software package is available, and the parameters they set is it turns out to be so small that it effectively they are solving for these extreme points, although they are using variational methods or variational machinery to do that. Whereas this is so the high level idea here is that a lot of these mixed membership models have a certain separable structure, and that separable structure should be exploited in a very clean way you can get good complexity results by doing that. That's perhaps the point that I'm trying to.
Just on that point about the separability. So for the Mallows model, each topic has a separate permutation, and then there's kind of noise around that permutation, right?
Yes.
So the large Q giving you the approximate separability corresponds to, even though the permutations might be identical essentially everywhere, there's noise.
So separability emerges. No, actually it's even simpler than that. So let me go back to this picture. Here. So look at this probability of this permutation sigma given the underlying permutation sigma j. This grows as phi to the power distance between the two permutations sigma and sigma j. What does this mean? It means that the probability that I'm going to have L flips. So supposing I have a ranking of 1 and ranking of L, okay, and there is a distance of L. The probability I'm going to flip L times is going down exponentially fast. So no matter how I generate, there is going to be 1 versus L is going to be very, very small probability that it is going to be L comma 1. And that is how you're getting approximate separability. So if I have 1, and if I have in the baseline model sigma j, if I have a 1 and if I have L and there is a distance of L minus 1, then this probability that I'm going to see L and 1 flipped is going to go down exponentially with the distance between the rankings. So eventually there is going to be at least that row where you're going to get something large and something small along that row.
That's only true if you use a Kendall tau when you have a JSON.
Yes, this is for Kendall tau. So the Mallows model is talking about Kendall tau.
And Mallows takes any distance function.
Yeah, so here I am talking about Kendall tau distance, right?
Right.